Open up your desktop computer right now, or peek inside the back of an old television, and you'll see dozens of these tiny metallic cylinders standing on the green circuit board.
Yeah, they look like little miniature grain silos, basically.
Exactly. And we usually just assume they're, solid, boring chunks of metal, perfect little mathematical monuments of silicon and copper.
Right. But they really aren't. Not at all.
No, they aren't. Because today, on this deep dive, we're going to reveal how those little towers are actually pressurized chemical tanks. We want to show you how they're responsible for, historical corporate espionage, explosive motherboard failures, and holding these weird ghost charges that can actually outlive the device itself.
It's wild stuff.
We're so glad you could join us today. Our mission is pulling from a remarkably dense, comprehensive, and surprisingly dramatic Wikipedia article all about the aluminum electrolytic capacitor. We're taking you right inside this ubiquitous little component to see how it works, how it fails, and why the tech industry literally cannot survive without it.
Yeah.
Okay, let's unpack this. Before we get into the literal explosions in the skull and recipes, we have to understand the magic trick that allows these tiny things to pack such a massive electrical punch.
What's fascinating here is that those little towers, the capacitors, aren't passive pieces of hardware at all. They are incredibly active, delicate chemical ecosystems. I mean, they are the wet, messy analog reality that keeps our seemingly pristine digital world running.
Which sounds like an oxymoron, right? Wet electronics.
Yeah, exactly. But it really is a feat of modern materials science. To grasp what's happening inside that little cylinder, you have to look at what a capacitor fundamentally does. In its absolute simplest form, a capacitor stores electrical energy between two conductive plates which are separated by an insulator. And we call that insulator a dielectric.
Right. And the general rule of thumb for storing that energy is pretty straightforward. If you want to store a lot of energy, meaning you want higher capacitance, you need a massive surface area for those two conductive plates, and you need the insulating gap between them to be microscopically thin. So it's basically a real estate problem.
It is entirely a real estate problem. The capacitance formula basically dictates that it's all about maximizing the area and minimizing the gap. But how do you fit the surface area of a large sheet of metal into a component the size of a pencil eraser?
Which seems physically impossible.
Right, but that brings us to the first genius move of the aluminum electrolytic capacitor. The positive plate, the anode, is made of pure aluminum foil. But instead of leaving it smooth, manufacturers put it through this intensive electrochemical etching process.
And when you say etching, I usually think of, lightly scratching a surface. But according to our source, this is vastly more extreme.
Oh, yeah, very extreme.
They submerge the foil in an acid bath and run a highly controlled electrical current through it. The acid literally eats away at the aluminum, carving out these microscopic deep tunnels and jagged valleys. It turns a flat sheet of metal into a microscopic sponge, multiplying the effective surface area by a staggering factor of up to 200.
Yeah, think of it like a microscopic dam. The rougher and wider the surface of the dam, the more water, or in this case electrons, you can hold back. By turning that flat foil into a sponge-like maze, you provide 200 times more physical space for electrons to gather.
Wow, okay. So we have our massive surface area, but then we need that incredibly thin gap, the dielectric insulator. And I'm assuming if you want the gap to be perfectly uniform over all those microscopic jagged peaks and valleys, you can't just slide a piece of paper in there. You have to actually grow the insulator directly out of the metal itself.
That is the exact mechanism, yeah. They use a process called anodization. By running a specific voltage through that spongy aluminum in a chemical bath, they force a layer of aluminum oxide to grow over every single microscopic peak and down into every single tunnel.
And this layer is thin, right?
Insanely thin. For the amorphous oxide type, it grows at a rate of about 1.4 nanometers per volt applied.
To put 1.4 nanometers in perspective for you, a single strand of human DNA is about 2.5 nanometers wide. So this insulating barrier, which is actively holding back the electrical charge, is literally thinner than a strand of DNA.
Which is just mind-blowing.
It is. It's like taking a piece of paper the size of a football field, crumpling it up at a microscopic level, and stuffing it into a matchbox, all while keeping the layers separated by a gap thinner than a DNA strand.
It's a brilliant piece of engineering, but it immediately creates a massive physical problem. You now have this incredibly complex, microscopic, sponge-like surface covered in a DNA-thin layer of glass-like oxide.
Right.
So how on earth do you get a second solid metal plate to perfectly press up against all those microscopic peaks and valleys to complete the circuit? If you just slap another piece of flat foil against it, it will only touch the very highest microscopic peaks. You'd lose all that surface area you just worked so hard to carve out.
And here's the punchline. You don't use a solid plate at all. You use a liquid. The actual second plate, the cathode, is a liquid electrolyte. Because it's a fluid, it effortlessly flows into every single microscopic crevice, molding itself exactly to that huge rough surface.
Exactly. That liquid is the true working cathode. The second aluminum foil you find inside the capacitor, which, most people mistakenly assume is the second plate, is really just a terminal.
Oh, so it's just there to make contact.
Right. It's just a piece of metal dipping into the liquid to carry the electrical current to the outside world.
It makes perfect sense when you lay out the physics of it. A liquid is the only way to make contact with a microscopic sponge. But it also begs a historical question. Who actually looked at a dry, solid electronic circuit and thought, you know what this needs? A puddle.
A puddle. Yeah, well, to find that pioneer, you have to go all the way back to 1875. A French researcher named Eugène Ducretet was experimenting with different metals and liquids, and he discovered what he called valve metals.
Valve metals.
Yeah, he noticed that when aluminum is placed in certain liquid baths, it acts like a one-way valve for electricity. It blocks current in one direction by rapidly growing that oxide layer we mentioned, but lets it flow freely in the other.
Fascinating. And then, in 1896, Carol Pollack took that valve idea and patented the first actual liquid capacitor. But these early versions weren't tiny cylinders, were they?
No, not at all. They were literally metallic tubs or heavy glass jars filled with a sloshing borax and water solution with a folded piece of aluminum sitting in them.
That sounds incredibly dangerous.
It was definitely clunky, but those giant wet tubs were absolutely critical for early telephone exchanges in the 1920s. See, early electrical grids and telephone lines suffered from terrible buzzing noises because alternating current AC power has a natural ripple to it. It's not a perfectly smooth flow of energy.
Right, it goes back and forth.
Exactly. By hooking up these large tubs of liquid borax, the capacitors acted like electrical shock absorbers. They soaked up the ripples and released the energy smoothly, eliminating the buzz.
But obviously, you can't put an open tub of sloshing borax water inside a consumer device that might get bumped or tipped over in someone's living room. Which brings us to 1925 and an inventor named Samuel Ruben,
who partnered with Philip Mallory, whose company, fun fact, eventually became Duracell.
Oh, wow, I didn't know that. But yeah, Ruben invents the quote-unquote dry electrolytic capacitor. He took the two aluminum foils, put a spacer of highly absorbent paper between them, soaked that paper in the liquid electrolyte, and rolled the whole thing up into a tight little cylinder.
And that rolled-up compact design is the direct ancestor of what sits on your computer's motherboard today.
I have to pause here, though, because looking at the source material, the dry capacitor that revolutionized electronics isn't actually dry at all. It's literally just a wet paper towel rolled up tightly inside an aluminum can. Dry is a total lie.
It is a complete misnomer. Dry in the 1920s context just meant it didn't have a pool of free sloshing liquid that could spill on your rug. It was still very much wet, relying entirely on that liquid-soaked paper spacer. But if we connect this to the bigger picture, that single, somewhat misleading mechanical shift changed the world.
How so?
By rolling the liquid up in paper, Ruben drastically reduced the physical size and the manufacturing cost. Suddenly, the bulky, expensive electrical buffers needed to build an AC-powered home radio could fit in a small box and be mass-produced. It's the breakthrough that transformed radio broadcasting from a niche hobby into a mass-market phenomenon.
So the Roaring '20s were essentially powered by rolled-up wet paper towels. But when we take a step back and think about the reality of sealing wet paper towels soaked in conductive chemicals inside airtight metal cans, that sounds less like an electronic component, more like a recipe for a bomb.
It is an inherent danger of the design, absolutely. Aluminum electrolytic capacitors are polarized. Because that insulating oxide layer is grown by applying voltage in a specific direction, it only works in that direction. The anode must always be positive, and the liquid cathode must always be negative.
So if a manufacturer wires it backward, or if someone mistakenly applies alternating current where the positive and negative keep flipping back and forth, the chemistry revolves.
Violently. If you apply reverse polarity, the chemistry starts working in reverse. That incredibly thin natural oxide layer on the cathode foil suddenly starts to grow rapidly. And the byproduct of that rapid chemical growth is hydrogen gas. Remember, This whole rolled-up system is sealed tight inside an aluminum can.
The pressure has nowhere to go.
The pressure builds up exponentially. If it goes unchecked, the aluminum casing can't hold it. The capacitor will literally detonate, blowing the metal casing apart like shrapnel.
Which is why if you look at the top of almost any modern capacitor, you'll see these little XK or T-shaped grooves snapped directly into the metal roof. That's a built-in pressure relief vent, right?
Exactly. When the hydrogen gas pressure hits a critical threshold, the can safely splits open along those weak points and hisses out the gas, rather than blowing a crater in your motherboard.
It's a vital safety feature. But sometimes, even the vents aren't enough to prevent a total catastrophe. Here's where it gets really interesting.
Oh, the capacitor plague.
Yes. If you owned a desktop computer, a television, or even a video game console between the years 2000 and 2005, and it suddenly died with a loud pop and smelled like fish, you were likely a victim of this exact phenomenon.
The tech industry experienced a massive, unprecedented wave of failures. Millions of power supplies and motherboards were just dropping dead. Technicians were opening up these machines and finding the capacitors bulging, popped open, and leaking a crusty brown sludge.
And according to our source, it wasn't just a random manufacturing glitch. It was corporate espionage gone terribly wrong. A scientist allegedly stole the recipe for a newly developed, highly conductive, water-based electrolyte from a Japanese manufacturer. They took the stolen recipe and sold it to mass-market component makers in Taiwan, who then churned out millions of these cheap capacitors for the global market.
But the thief missed a crucial detail. The recipe they stole was incomplete. It was missing specific, highly proprietary stabilizing additives.
Why are stabilizers so important if the base liquid is just water and some salts?
Because water and raw aluminum do not get along. When water and aluminum mix without those delicate stabilizing chemicals balancing the reaction, the water attacks the metal. It's not just a slow evaporation. It is an aggressive, destructive chemical reaction.
Yikes.
Yeah, the water actively corrodes the aluminum, generating massive amounts of internal heat and hydrogen gas from the inside out.
It's a stark reminder that this component is fundamentally a contained chemical reaction. It's a tightrope walk between achieving high electrical conductivity and triggering destructive corrosion. And because of one stolen, incomplete recipe, it cost the tech industry millions, if not billions of dollars to recall and replace all those ticking time bombs.
It perfectly illustrates the fragility of the ecosystem inside that tiny can.
So a bad recipe turns it into a bomb.
Yeah.
But let's say you have a perfectly manufactured capacitor from the best factory on Earth, and it's wired correctly. It still has a fatal flaw. Every single wet electrolytic capacitor has a ticking clock inside it.
Because it relies on that liquid-soaked paper, and because no rubber seal at the bottom of the can is absolutely perfect, the liquid electrolyte slowly, inevitably evaporates over time. It literally dries out.
And as it dries out, the physical pathways for the electricity to flow start to disappear. The source mentions a term here, equivalent series resistance, or ESR.
That's the critical metric. Imagine a multi-lane highway. The liquid electrolyte provides millions of microscopic lanes for electrons to travel into those etched valleys. As the liquid evaporates, lanes start closing. The electrons get bottlenecked. That bottleneck is electrical resistance, the ESR going up.
And whenever you have electrical resistance, you get friction, you get heat.
Exactly. When you have alternating current rippling through the capacitor, what engineers call ripple current, pushing through that bottleneck generates internal heat. That heat then speeds up the evaporation of the remaining liquid, which raises the resistance even further, which creates even more heat. It's a slow, unavoidable death spiral.
So heat is the ultimate enemy.
Yeah.
And I'm assuming there's a direct mathematical correlation here. Like, if my computer runs a little hot because the fan is dusty, I lose a few weeks of lifespan on the hardware.
It's actually much more dramatic than that. It's an exponential curve known in the industry as the 10-degree rule, which is derived from the Arrhenius equation.
Okay, lay that out for me.
Well, heat is essentially molecular vibration. Adding just 10 degrees Celsius doesn't just make the liquid slightly warmer. It pushes a massive threshold of the liquid molecules past the energy barrier required to break free and turn into gas.
So what does that mean for the lifespan of the component?
The rule is remarkably brutal. For every 10 degrees Celsius you drop the operating temperature, the rate of evaporation halves, meaning you effectively double the capacitor's lifespan.
Wait, really? Double?
Double. So if a capacitor is rated by the factory to survive 2,000 hours at a boiling 105 degrees Celsius, if you can design your circuit board to keep it at a cool 45 degrees, that exact same capacitor will last for about 15 years.
Wow. So it's like keeping a block of ice in a cooler. If you design your circuit board with good airflow to keep it cool, the capacitor lives for decades. If you cram it next to a hot microchip, it dries up and dies. The placement of a capacitor on a circuit board isn't just about where it fits. It's a life-or-death thermal calculation.
Yes. Engineers literally use this 10-degree formula to calculate the survival probability of your electronics, a metric known as FET, or failures in time.
But the liquid isn't just a flaw that causes it to die, right? The source points out an incredible paradox. The liquid is also a healer.
That is the beautiful irony of the design. The liquid that eventually evaporates and kills the capacitor is the exact same thing keeping it alive day to day.
How does that work?
Well, if there's a sudden voltage spike in your power supply and a microcrack forms in that ultra-thin, DNA-sized aluminum oxide dielectric, the capacitor would normally short out immediately. The device would be dead. But the liquid electrolyte contains oxygen.
So it reacts.
Exactly. The very millisecond a microcrack exposes the raw aluminum underneath, the liquid reacts with it and instantly anodizes a brand new layer of oxide over the wound. Cell heals in real time.
It's like a tiny metallic immune system. The fluid rushes to the site of the injury and scabs it over with glass.
It is a perfect self-repair mechanism, and purely solid-state components simply cannot do that the way these wet ones can.
So they heat up, they slowly evaporate, they heal their own molecular wounds, and sometimes they explode. But what happens when they are completely dead? When you unplug the device and throw it in the closet, the source mentions a phenomenon called dielectric absorption, or soakage.
It's one of the most counterintuitive behaviors in electronics. You take a capacitor that has been powered on and charged up for a long time, you unplug the device, and a technician deliberately shorts the capacitor to completely discharge it. The voltage reads absolute zero. By all laws of basic physics, it should be dead.
But it's not.
Nope. If you remove the short and just let it sit there on the workbench, the capacitor will mysteriously develop a small electrical voltage all on its own.
So what does this all mean? Does this mean my unplugged PV is still technically holding a grudge?
In a way, yes. It's also known as battery action. To understand what's happening, you have to look at the molecules inside the dielectric insulator. It's a process called time-delayed dipole discharging.
Let me see if I can picture this. If the molecules in the dielectric are dipoles, they have a positive end and a negative end, like tiny compass needles.
That's a great way to visualize it. Imagine thousands of tiny compass needles embedded in the material. When the power is on for hours or days, the sheer force of the voltage forces all those microscopic needles to twist and point firmly in one direction. They physically stressed into alignment.
And when you unplug it and discharge the energy quickly, the energy in the plates is gone, but the physical needles themselves take time to relax.
Exactly. The main electrical charge leaves instantly, but those physical molecules are deeply embedded in the material. They don't just instantly snap back. Over hours or even days, they slowly drift and twist back into their natural resting state.
And that movement generates power.
Yes. As they physically move, that motion pushes a tiny bit of residual ghost electricity back into the conductive plates.
This raises an important question. Is that dangerous? If I touch a circuit board from a TV that's been in the attic for a week, am I going to get zapped by ghost electricity?
In a small consumer radio or a TV board, the soakage voltage is very low. It might just cause a faint, surprising pop in a speaker. But in massive, high-voltage industrial capacitors, the kind used in power grids or heavy machinery, this ghost voltage can actually creep up high enough to deliver a lethal shock to a technician days after the machine was completely disconnected from power.
That's terrifying.
It is a serious hazard. That is why large high-voltage capacitors are actually shipped from the factory with a thick shorting wire physically wrapped around the terminals. You have to manually remove that wire right before you install it, just to ensure it hasn't soaked up a dangerous ghost charge while sitting in the cardboard box.
It's a perfect example of how the ideal, clean physics we learn in the textbook, where a discharged capacitor is a mathematically empty bucket, clashes with the messy reality of physical materials. The material itself literally remembers the charge.
The physical world always leaves a trace.
Well, we have covered an immense amount of ground today. From the genius of taking a flat piece of aluminum foil, chemically eating it away to be 200 times rougher, and coating it in a glass-like barrier thinner than human DNA. We've seen how rolling up a wet paper towel in 1925 accidentally paved the way for mass-market consumer radios.
And we've explored the darker side of the chemistry, The capacitor plague, the violent potential of missing stabilizers, and the absolute necessity of stamping pressure vents into the metal casing.
We looked at the ticking clock of the Arrhenius 10-degree rule, seeing how molecular vibration slowly boils away the component's lifeblood, even as that exact same liquid desperately rushes to self-heal the microscopic cracks inside. And we ended with the spooky reality of time-delayed dipoles and lethal ghost voltages.
It is a component defined entirely by its contradictions. It is the heart of our electronic world, yet it relies on archaic liquid chemistry. It is incredibly fragile, yet it is trusted to power almost every device on Earth.
So next time you look at a green circuit board and see those little aluminum towers standing there, you aren't just looking at solid pieces of metal anymore. You know you're looking at tiny, pressurized chemical tanks doing the heavy, dangerous lifting for your digital life.
They truly are the unsung, hardworking heroes of the hardware world.
But I want to leave you with one final provocative thought, based on where the tech industry is desperately trying to head. Because hardware manufacturers absolutely hate the evaporation problem. They hate that ticking clock. They are actively trying to replace these wet liquid electrolytes with completely solid conductive polymers, using advanced materials like PD. And because these polymers are solid, they don't evaporate.
Right, they completely solve the drying out problem and eliminate the ESR death spiral.
But as we learned today, the solid types completely lack the incredible instantaneous oxygen-based self-healing properties of the wet liquid. So here is something to ponder. If material science can ever invent a completely solid polymer that can perfectly self-heal its own molecular runes the way a sloshing liquid does, we might finally cross the threshold into creating consumer electronics with literally immortal power supplies.
Now that is a fascinating prospect for the future of engineering.
And until someone invents that magical mortal polymer, we will just keep relying on our tiny pressurized chemical tanks. Thank you for joining us on this deep dive.